Now, let's talk about the properties of determinant. That would be section 2.2. So in this session, we will introduce several properties that are related to determinant. So the first one, that is lemma 2.2.1. If the matrix A is an n by n matrix, and if we call AJK as the cofactor for the entry small ajk, okay, then we know that we can do cofactor expansion. So AI1 capital AJ1 plus AI2 capital AJ2 to AIN to times capital AJN. It is equal to determinant of A if I is equal to J. That means if we multiply the entry with the corresponding cofactor, then we really do the cofactor expansion. However, if I is not equal to J, that means if we intentionally multiply an entry with incorrect cofactor, then the result will be equal to 0. So this is the so-called lemma 2.2.1. Okay. So how can we prove it? Okay. If I is equal to J, it is just like a cofactor expansion along the ith row of the matrix A, right? So if I is equal to J, then the equation becomes AI1 times capital AI1 plus AI2 times capital AI2 and so on. So this is a formal formulation for the cofactor expansion along the ith row, right? However, if I is not equal to J, so how can we prove it? Okay, so now we get another matrix called A star. A star be the matrix obtained by replacing the jth row of A by the ith row of A. So assume this row originally it is the jth row of A. Now if we replace this jth row by the ith row of A, it becomes this row is AI1, AI2 to AIN, and this is called the jth row. And the original ith row here is AI1, AI2 to AIN. We call this matrix as A star. So we would like to calculate the determinant of A star. Okay, and because A star has two rows of the same, that means this matrix A star has two identical rows. And according to the property we have mentioned before, we know that the determinant of A star is equal to 0, right? Okay, so if we expand A star along the jth row, then the formulation would be like 0 is equal to the determinant of A star. So this is the property we mentioned in section 2.1. And if we do cofactor expansion along the jth row of A star, it is like we do cofactor expansion along this row, right? So the calculation would be like AI1 times A star J1. Why? Because originally this is called AJ1, and because we have already replaced in the original matrix A, it is called small aj1, right? But now for A star, the aj1 is replaced by AI1. Okay, so the cofactor corresponding to this entry is capital A, is the A star J1, right? So if we remove this row and this column, the remaining submatrix is called is actually the A star J1. So the corresponding cofactor is this one, right? And then we do cofactor expansion along the jth row. That would be AI2 times A star J2 and so on. Okay, and if you look at the A star J1 carefully, you will find that actually this is equal to AJ1, right? And this is equal to AJ2. So A star J2 is equal to AJ2. A star J1 is equal to AJ1. Okay, if you cannot imagine the equality, then you may need to use some real example and do this kinds of calculation, and you can easily figure out this. Okay, so we can rearrange the original calculation as this one. And what is this? This is AI1 times capital AJ1 plus AI2 times capital AJ2, where I is not equal to J. And we can see that the result of this calculation is equal to 0. Okay, so this lemma tells us that if we do the cofactor expansion, if we times the entry with the correct cofactor, then the result is the determinant. However, if we intentionally times the entry with incorrect cofactor, then the result would be equal to 0. Okay, so this is the lemma 221. Okay, so we can prove this lemma in this way. Next, we would like to discuss how elementary row operation change the value of the determinant. Okay, so let's consider the elementary row operation number 1, type 1. That would be we interchange two rows. Okay, so originally we are given this 3 by 3 matrix, so we can subtract the second row from the third row. Okay, so the we can reduce just like we do the elementary row operations through the type 3 elementary row operation. So we subtract the second row from the third row. So after this operation, we get this new matrix, right? And then we add the second row to the third row. So the third row becomes this one, A21, A22, A23. And then the second row is subtract from the third row. Okay, so the second row becomes minus A31, minus A32, and minus A33. And then we multiply the second row with minus 1. So it becomes A31, A32, and A33. So if you look at this resulting matrix, you can see that actually this result is just like we interchange the second row and the third row, right? Okay, so the A4, the matrix A4 is the result of we interchange the second row and the third row. And we can see that actually interchange two rows can be implemented by a sequence of elementary matrix type 3, elementary row operation type 3. That means we can add a row by a multiple of another row, right? So the determinant of the original matrix A is equal to A1 and A2 and A3. So if you look at carefully, A1 is to the type 3 row operation. A2 is also type 3 operation. A2 is also A2 and A3. They are all involved with type 3 operation. Okay, so only the A4 is the type 2 operation, right? And in fact, if we do the type 3 operations on a matrix, the determinant would not change. Okay, so this part will be shown later. Okay, and the type 3 operator. Okay, the result of type 3 operator is actually we put we multiply with -1 with the original determinant. So the determinant A4 is actually equal to minus determinant A3, and is also equal to minus determinant A. Okay, so based on this calculation, let Eij form from I by interchange the ith row and the jth row, and we can see that actually if we interchange two rows, that would change the sign of the determinant. Okay, so these kinds of type 1 elementary matrix, the determinant of Eij is equal to the determinant of Eij times I, right? And the interchange make the sign change. So we multiply with -1 and then times determinant I. And we know that determinant I is equal to 1. So the result is equal to -1. Okay. Then if we interchange two rows of a matrix A, how can we implement it? Okay, we implement with Eij pre-multiply with the matrix A, right? And this make, how about the determinant of the result matrix? Okay, this make the determinant of A, we multiply with -1. Okay, multiply with -1. Okay, so this is the result of if we interchange two rows. Okay, and what is minus determinant A, which is equal to, we already know the Eij, the determinant of Eij is equal to -1. So actually, this result is equal to determinant Eij times determinant A. Okay, so remember this. This is also another important property. Okay, if we multiply two non-singular matrices, actually we will prove that. We will prove it later. Okay, if we in this case, we just say this case. In this case, okay, if we interchange the matrix, the two rows of matrix A, then it would cause the determinant sign change. Okay, it will change the sign of the determinant A. Okay, so this is what we know for the row operation number 1. Okay, that will make sign change. Row number 2, that means a row of A is multiplied with a non-zero constant. Okay, so that E denote the elementary matrix formed from I by multiplying the ith row by the non-zero constant alpha. Okay, then the result would be equal to these kinds of elementary matrix. Each determinant is equal to determinant of E times I, which is equal to alpha times determinant I, which is equal to alpha. Okay, so we can check why. Okay, if we pre-multiply these kinds of E with A, then we try to calculate the determinant EA. So the result of EA, we call it A2, would be like this, right? We multiply the ith row with alpha. So how can we calculate this determinant? Actually, we can do coefficient expansion along this row, right? So the determinant EA is equal to alpha AI1 times capital AI1 plus alpha AI2 times capital AI2, and so on, right? So if we take alpha out, then the the process in the parenthesis is actually determinant A. So determinant EA is equal to alpha times determinant A, which is also equal to determinant E times determinant A. Okay, so this is the inference of type 2 row operation. Then, the most important one is type 3. Okay, type 3 means a multiple of one row is added to another row. Okay, so we would like to derive the property of how these kinds of operation change the determinant. Okay, so if E is formed from I by adding C times the I's row to the J's row, then the determinant of E is equal to 1. Okay, we would like to show this. Okay, so if we pre-multiply these kinds of matrix E with A, then if we do cofactor expansion along the J's row, okay, then the we do the the cofactor the J's row. The J's row would be the AJI plus CAI1. Okay, because we times the I's row and then add it to the J's row. So the entry of the J's row would becomes AJ1 plus CAI1. Right? And if we do cofactor expansion, this entry times capital AJ1, and this entry times capital AJ2, and so on. Right? And then we do some rearrangement. We take AJ1, capital AJ1, plus AJ2 times capital AJ2 together. So this is the first part. And then the second part would be, if we take the C out, then the second part becomes AI1 times capital AJ1 plus AI2 times capital AJ2, and so on. Right. And according to lemma 221, remember that if we multiply the entry with incorrect cofactor, the result will be equal to 0. Right? So the second part will be equal to 0. Okay, the second part will be equal to 0. So the result here is actually equal to the determinant of A. So that we know determinant of EA is equal to determinant of A. Okay, and this is equal to determinant E times determinant A. Okay, and you may wonder why the original elementary matrix E, its determinant is equal to 1, because you can check the theory 2.1.3. Okay, so for the elementary, the third type elementary matrix, it would be like lower triangular matrix or upper triangular matrix, right? And according to theory 2.1.3, we know that for any triangular matrix, its determinant is equal to the product of the diagonal element, right? And please go to check elementary matrix of type 3. It's actually a lower triangular matrix or an upper triangular matrix. So its determinant should be equal to 1. Okay, so this is why we can write down determinant A is equal to determinant E times determinant of A. Okay, so in summary, no matter which type of row operation, we can write down determinant EA is equal to determinant E times determinant A, right? So this is for the type 3. And this is for type 2, right? For type 2, we also can write it down like this. And for type 1, we can also write it down like this, right? So in summary, if with that E denote the elementary matrix of a row operation, then determinant of EA is equal to determinant E times determinant A. And if the E is of type 1, then determinant E is equal to -1. If E is of type 2, then determinant E is equal to alpha, where alpha is a non-zero scatter. If the matrix E is of type 3, then determinant of E is equal to 1. Okay, so this is how different elementary row operations influence the determinant of a matrix. Right? And similar result also hold for column operation. Okay, indeed, because if E is an elementary matrix, then E transpose is also an elementary matrix. Okay, we can show that. So if we post multiply these kinds of matrix E with the matrix A, okay, so determinant AE is equal to determinant the transpose of AE. Okay, we already showed this before, right? A matrix, the determinant of a matrix is equal to the determinant of its transpose, right? So this becomes determinant of E transpose times A transpose, okay? And this can be rewritten as determinant E transpose times determinant A transpose, which is equal to determinant E times determinant A. Okay, so this kinds of relation also holds for the column operation. But in most cases in linear algebra, we work on elementary row operations in most cases. Okay. So another summary is that the effects that row or column operations has on the value of determinant can be summarized as follows. First, interchange two rows of a matrix, change the sign of the determinant. Okay. Second, multiply a single row of a matrix by a scatter has the effect of multiplying the value alpha of the determinant by that scatter alpha. Right. Third, adding a multiple of one row to another does not change the value of the determinant. Okay, so this would be very important property of determinant. Okay, now we will introduce more properties. Okay, an n by n matrix A is singular if and only if determinant of A is equal to 0. Actually, this is the main reason why we want to define the calculation of determinant, because we want to define a value. If this value is not equal to 0, then the corresponding matrix is non-singular. If the value or the determinant of a matrix is equal to 0, then this matrix is singular. Okay, so now we want to from the opposite position, we want to prove that if n by n matrix A is singular, if and only if its determinant is equal to 0. Okay, So how can we prove it? Okay, that the matrix U as the reduced row echelon form of A. That means we can do a sequence of elementary row operations on A to reduce A into U, right? And now, the determinant of U, according to what we mentioned in previous slides, we know determinant U is equal to determinant EK times determinant EK minus 1 to determinant A, right? And we know all the determinants of all the elementary matrices are not equal to 0, right? We know this. The determinant of any type of elementary matrix is not equal to 0. Here, it would be minus 1, it would be non-zero value, or it would be 1. So the determinant of E is never equal to 0. Okay. So the determinant of EI would be never equal to 0. So how would determinant U equal to 0 if and only if determinant A is equal to 0? Okay, so if determinant A is equal to 0, then determinant U is also equal to 0. If determinant of A is not equal to 0, then determinant U is not equal to 0 either, right? Then if A is singular, then U has at least one row consistently of entirely of zeros. That means if A is singular, then if we reduce A into the reduced row echelon form, then the matrix U would has at least one row consisting entirely of zeros. Okay, so in that case, determinant U is equal to 0, because we already know that if some matrix contains at least one rows containing entirely of zeros, then its determinant is equal to 0, right? Because we can do coefficient expansion along that 0 row. Okay, and if A is non-singular, then U is triangular with 1 along the diagonal. That is looking like this. Okay, if A is non-singular, then its corresponding reduced row echelon form would be looking like this. Okay, so we can see that this kind of matrix is a upper triangular, is a triangular matrix, right? And its diagonal entries are all equal to 1. So the determinant U is equal to 1. Okay. So this is how we prove that the theory 222. Okay. N by N matrix A is singular if and only if determinant A is equal to 0.好，这边我们用中文再重讲一次哈。好，我们要去证明一个矩阵 A， 它如果是 singular 的话，它的行列式就等于0，或者反过来讲，它的行列式等于0的话，它一定是 singular， 它一定不可逆。好，那怎么证明呢？我们就把 A 呢经过一系列的基本列运算，转成 reduce row echelon form U。好，那你如果还记得 reduce row echelon form 意思就是你把对角线上面的值，对角线以下的值都等于0，对角线上面的值都刚好等于1， 对角线上面的值呢，可能会有一些非零的数值，这样好。那这样的矩阵 U 呢，就可以写成一系列的基本矩阵乘在这个矩阵 A 之前。好，那这个矩阵 U 的行列式就会等于是这些基本矩阵的行列式相乘，再乘上 A 的行列式。好，那因为基本矩阵的行列式一定都不等于0啊，所以说呢 ，determinant U 是不是等于0，就取决于 determinant A 是不是等于0。OK， 好，所以我们现在呢，把 determinant U 跟 A 的这个关系已经完全让它等同同义化了。好，那接下来，如果 A 是 singular， 好，就代表 A 是不可逆的。如果 A 是 singular， 根据我们过去的经验，我们就知道说呢，我们把 A 变成 reduced row echelon form U 的时候，这时候的 U 呢，至少会有一列全部为0。OK， 至少会有一列全部为0。啊，这个你可以在过去，你可以去回顾一下定理152。定理152讲这件事。好，那如果说 U 有一列全部为0，那就代表 U 的行列式一定等于0，对不对？因为我们如何去算 U 的行列式？我们可以针对全部为0的这一列去做 cofactor expansion 嘛，所以它行列式一定等于0嘛。那 U 的行列式如果等于0，就代表 A 的行就代表 A 的行列式也一定等于0，对不对？因为我们上一页已经把 U 的行列式跟 A 的行列式把它等同化了。好，所以也就是说，这句话告诉我们，如果 A 是 singular， 那么 A 的行列式就等于0。OK， 好，那如果 A 它是可逆的，它是 non-singular， 那根据我们之前一样，根据定理152以及我们之前的其中一个证明，如果 A 是可逆的，那么 U 经过一系列的基本列运算 reduce 之后，它一定是一个三角矩阵，然后呢，它的行列式上面的值都等于1。好，那在这样的情况之下，这个 U 的行列式呢是等于多少？就等于是对角线上面的数字相乘，所以它行列式一定等于1。好，也就是说，如果 U 的行列式等于1，那么 A 的行列式呢？A 的行列式不一定等于1啦，但是我们只能够说 U 的行列式不等于0，那么 A 的行列式也一定不等于0。所以这句话就告诉我们说，如果 A 是non-singular 的，是可逆的，那么 A 的行列式呢也是不等于0。这样子。Okay, so this is the theory proof of theory 222. We can also use another way to show this proof. Okay, another way to compute determinant of A is reduce A to row echelon form. Okay, if the last row of U consists entirely of 0, then A is singular and the determinant A is equal to 0. Okay, so from the beginning to now, it's exactly the same as what we mentioned before. Okay. Otherwise, A is non-singular, and its determinant is equal to the receptor. It is equal to the inverse of the determinant, the product of this elementary matrix. Okay. We can also show this. Okay. 好，这边有点奇怪啊，就是说这里在做什么呢？Another way to compute determinant A 就是 A 的行列式要怎么算？好，那首先呢，我们知道说我们可以把 A 呢经过一系列基本列运算变成是 U。好，如果 U 的最后一列全部为零，那 U 的行列式就等于零嘛。好，那这时候呢 A 的行列式呢也会等于零，因为 determinant U 等于是这些东西乘在一起。好，因为等号左边等于零嘛。好，所以然后呢，因为这些 elementary matrix 的 determinant 都不等于零 ，OK， 那这些人都不等于零，那凭什么 determinant U 这里等号左边会等于零呢？那就是你的 determinant A 要等于零嘛。OK， 啊，这是一种状况。好，那如果今天 determinant U 不等于零，好 ，determinant U 不等于零的话，那么 determinant A 也一定不等于零。好，那你也不用担心它前面乘的这些 elementary matrix 的 determinant 会等于零，因为它们根据定义，它们就不会等于零嘛。好，那所以到底 determinant A 的值是什么呢？你如果以这个实数的计算来讲，你可以把它想象成，其实就是把这一坨数字除过来嘛。好，除过来。好，所以说呢，determinant U 会等于1，那你就对它把这些值除到左边来，就变成是分母，也就相当于是取实数的那个导数的意思。好，所以说，这里其实就是这个导数的意思。所以 determinant A 呢，其实就是 determinant EK 乘上 determinant EK 减1，一直到 determinant E1 的 inverse。但其实这些东西都是实数啦，实数的 inverse 其实就是取实数的导数的意思啦。OK， 那这个就是我们怎么去算出，如果 A 是 non-singular， 那么 determinant U 就会等于1。好，那 determinant A 实际上到底怎么算呢？你其实就是把这一堆 elementary matrix 的 determinant 乘完之后取导数，就是 determinant A。好，这里就是告诉我们一个方法，可以来计算 A 的行列式。OK。Actually, if A is non-singular, it's simpler to reduce A to triangular form using row operation 1, and type 3. Okay, so we can rely on interchange two rows or type 3 row operation to reduce A into a triangular form. Okay, so we can apply a sequence of elementary row operations to A to get a triangular matrix T. And because we already know that if we do type 1 or type 3 elementary row operations, the determinant would be multiplied with positive 1 or negative 1 here. Okay, if we just do type 1 row operation or type 3 row operation, then the inference would be multiplied with positive 1 or negative 1, right? So if we only use type 1 or type 3 row operations on A, then the determinant of T and the determinant of A, the relation between them would be positive 1 or negative 1. Okay? And because T is a triangular matrix, so the determinant of T is equal to the product of the diagonal entry. So if we call T11, T22, Tnn as the diagonal entry, then the result would be positive T11 to Tnn or negative T11 to TNN. Okay, so this is another special case. Okay, so let's try to see some real example. Okay, so originally this 3x3 matrix, if we do type 3 row operation, so this original determinant is equal to this one. So even if we have already reduced this by type 3 operation, the determinant is still the same, right? And then if we interchange the second row and the third row, we make it into a triangular matrix, right? And if we interchange two rows, remember we need to multiply with -1 before the determinant. And then if we can reduce the original matrix in this way, it would be very easy to calculate the determinant of this triangular matrix because we just multiply the diagonal entry. So that result would be -1 times 2 times -6 times -5, and the result would be -60. Okay, so this would be a very easy way for us to calculate the determinant. Now, we go to theory 223. Okay, if matrix A and B are both n by n matrices, then the determinant of AB is equal to determinant A times determinant B. Okay, so how can we prove it? First, if B is singular, then follows from theory 1.5.2 that the matrix AB is also singular. Okay, so if B is singular, then according to theory 1.5.2, then AB is also singular. Why? We can check this. Okay, if B is singular, then Bs equals to 0 has non-trivial solution. Right? We know this before. Then if we pre-multiply both sides with the matrix A, that would becomes ABX is equal to A0 is equal to 0, has non-trivial solution. Right? So this means the matrix A times B is also non-singular. Okay? So if B is singular, then AB is also singular. Then if AB is singular, then its determinant is equal to 0. Right? And the 0 is equal to determinant A times determinant B. Why? Because B is singular. So its determinant is equal to 0. So this equation must be satisfied. Okay? Got it? Okay. Then if B is non-singular, so B can be written as a product of an elementary matrix, right? So determinant AB can be written as determinant EK minus 1 to E1. Because B is non-singular, it can be written as a product of a sequence of elementary matrices, right? And this determinant can be written as determinant A times determinant EK times determinant EK minus 1 to determinant E1. This is what we know before, right? And because all these values are not equal to 0, they can be multiplied together first and then take the determinant. Okay, so this would be equal to matrix B. So the original determinant AB is equal to determinant A times determinant B. Okay, so based on this, we prove the theory 223. Okay, so you need to very carefully look at the proof from sentence to sentence to make sure you really understand why we can go from this statement to another statement. Right? So let's explain this in Chinese again. 好，所以在这个定理里面，我们要证明的是，如果 A、B 都是 n by n 的矩阵，那么 A、B 乘完之后的行列式等于是 A 的行列式乘上 B 的行列式。好，那我们要证明这件事情。好，那我们也不知道 A 跟 B 是不是可逆的，我们不知道。好，那我们就分两种状况来讨论。我们不管 A， 我们只管 B。好，如果 B 是不可逆的，它是 singular。好，如果 B 是 singular， 那么 A 乘 B 也会是 singular。好，为什么呢？我们看到最右上角，如果 B 是 singular， 那么它对应的 homogeneous system Bx 等于0，就会有 non-trivial solution。定理152是告诉我们说，如果 A 是 non-singular 的话 ，AS 等于0，就只有 trivial solution。好，那在这个继续延伸，其实我们之前也证明过 ，B 如果是 singular， 那么 BS 等于0呢，一定会有 non-trivial solution。之前的这个证明是来自于我如果把这个矩阵 B reduce 成 row echelon form 的时候 ，reduce 成一个矩阵 U 的时候，那个 U 呢就会出现 free variable， 就会出现那种自由的变数，好，那它就会有非零的解 ，BS 等于0就会有 non-trivial solution。好，那如果我们在等号左右两边都乘 A， 所以就变成 ABX 等于 A0， 就等于是零向量，代表说 ABX 呢就会有 non-trivial solution， 这个 X 可以有 non-trivial solution， 所以我们就知道说这个矩阵 AB 也是 singular。OK， 好，那如果 AB 这个矩阵 A 乘 B 乘完之后的这个矩阵是 singular， 那它的行列式的值就会等于0。好，那它等于0的话，那就代表说 determinant 0一定等于是 determinant A 乘 determinant B。为什么呢？因为 determinant B 一定等于0，所以我不管 determinant A 是多少，我 determinant B 一定等于0，所以这个式子一定成立。好，这个式子一定成立。好，那这是当 B 是 singular 的时候。那 B 如果是 non-singular 呢？好，那如果 B 是可逆的，那 B 就可以写成一系列的基本矩阵相乘，对吧？好，也就是说，这里有讲嘛，如果 B 是 non-singular， 那 B 呢就是 row equivalent to I， 那也就是说，它有办法经由一系列的基本列运算，把 B reduce 成 I 嘛。那也就是说呢 ，B 可以写成一系列的基本矩阵相乘嘛。好，所以 determinant AB 呢，就可以写成是 determinant A 乘上 1k 减 1k 减1等等等，一直到1万。好，那一个矩阵乘上一系列的基本列运算，根据我们之前所说的，它可以表达成它的行列式可以表达成这个。好，你只要是乘上基本列运算，你一定可以拆解成原本的 determinant A 乘上这个elementary matrix 的行列式。好，所以呢，它一定有办法拆解成这个样子。好，那你一系列的这些基本矩阵的行列式，它的值要么正一，要么负一，要么是阿尔法嘛。好，那这个行列式的值就会等于是我把这些基本矩阵乘在一起之后，再取行列式的结果。好，事实上，这一个点跟刚刚你从这里拆解成这个是一样的意思。你把其中一个当成 A， 那基本上是一样的意思，对不对？啊，比如说你把 EK 当成现在变成是好像是一个矩阵 A 的一个角色，你从这边拆解成这样，再从这里变回这里是一样的意思嘛？好，然后这个呢，这个是谁？这个其实乘起来，这个就是矩阵 B 啊，所以我们又证明了 determinant of AB is equal to determinant A times determinant B。OK， 好，所以这就是定理223的一个证明。OK，so yeah，so this is the end of session 2.2. We introduced several important properties and theorems about determinant.